Looking at lesson 6, we have a lot more Boolean algebra properties. Now, you could almost take a whole course on this really in college. So we're not going to go too deep into this. And if you want to read more about it, there's tons of things on the internet you could explore. This is a pretty good site. It's got a list of a lot of Boolean algebra properties. So, if you wanted to, you could look at this. You could dive a little deeper into this. These almost any site you go to is going to write these properties out differently. And what I mean by that is like they're going to use different symbols and notations. Like this one's using a plus sign for the or, and they're using a period for the and. Other sites might use an asterisk for the and. They're using an apostrophe for their not operator, okay, as opposed to an exclamation point like we do in Java. And anyway, there's all kinds of stuff. Now, the only one here that the College Board really wants you to know about is this one called DeMorgan's Law. And I'm going to go over that with you here in a minute. Okay, and so DeMorgan's Law, this is a common Boolean algebra law, talks about how we can change a not operator across an and or across an or. So we say that these two things are equivalent. You can say that the opposite of A and B taken together is equivalent to the opposite of A individually or the opposite of B. What does it mean to say that they're equivalent? Well, it means that for every combination you could come up with of A and B, given that they're Boolean, you would then be able to get the same outcome each and every time, whether you're talking about this left expression or this right expression. So if A and B were both true, they're going to evaluate the same. If they're both false, same evaluation. If A is true and B is false or vice versa, both of those expressions are still going to lead to the same overall evaluation. So that's what it means for them to be equivalent. Sometimes we show that through something called a truth table. CS Awesome has some nice examples of truth tables. You would never have to do a truth table on an AP test or on my test, but it's something that you may want to do to like check your work or to check if expressions are equivalent. And we'll talk about that as we do some problems together. So anyway, here's some examples of DeMorgan's law. Okay, so I've got here kind of a weird statement. I've got like some stuff going on here. X is 10, so that's true if you notice. Okay, here I've said y is less than or equal to 10. That's false. Now what DeMorgan's law says is that I could rewrite this big weird expression a little bit differently. I could take the not operator and apply it to that left term, and I could apply it to that right term. Okay, but to do that, it's not really like a distributive. It's not like this is math class and I'm distributing a 3. DeMorgan showed that that's equivalent expression provided that you change the logical operator and to or. Okay, so that's the key piece here. Now, one other thing I could do with this is I could take this even further in my Boolean logic, and I could say that it's equivalent to consider, not equals. I could actually just rewrite it as a not equal sign. Or what is the opposite of less than or equal to? Well, the opposite of less than or equal to is strictly greater than. And so I'm saying that this is an equivalent expression. Now, that wasn't really applying to Morgan's, so I didn't change the or operator back to an and. I just simply rewrote those expressions in a different way with that not operator. Here's another example. Okay, so here I have an or operator, and on the outside of my or operator, again, I have this not operator. Well, DeMorgan says that I can distribute that not operator to both sides, although it's not really a distributive property because I had to do another change. I had to change the or to an and. Now I could then rewrite those expressions again. Equals could become not equals in both cases. So what I'm predicting is that these first 3 prints are all going to match, and so is the next group of 3 prints. Notice that we got true for all 3 and we got false for all 3. That's what DeMorgan's is telling us, is that all of this stuff is just equivalent to each other. So it's just a different way that we could write these expressions. Okay, and sometimes if you start doing like circuit evaluation or things in another setting, you might want to, evaluate Booleans differently. Okay, so sometimes we prove these things through what we call a truth table. Like I mentioned a minute ago, a truth table is a way to like consider all of the possibilities imaginable. So I've got two Booleans here, A and B, and initially I've initialized them both to true. And I've gone ahead and I've printed out, notice that those are my two DeMorgan's pieces. DeMorgan says that the opposite of A or B is equivalent to the opposite of A and the opposite of B. That was one of our DeMorgan's properties that we saw right here. Actually, sorry, it was this one. Okay. And so what I've done now is I've gone through and I've initialized A and B to every possible combination I could come up with. I couldn't think of any others. Okay. They could both be true. They could both be false. A could be true while B was false. A could be false while B was true. That's it. And that makes sense. If you have two variables, two outcomes each, 2 times 2, there's only 4 combinations. If I bring in a third variable, there's going to be 8 combinations. If I bring in a fourth variable, now there's going to be 16 and so on. Okay. You learn that in math. That's like the product property or something. Okay. So anyway, if we look at this, notice that I got equivalent prints each time. So whether I was using not the quantity of A or B or not A and not B, I got the same outcome every time, regardless of the values that I chose for A and B. It was always the same. That's what it means to say that two Boolean expressions are equivalent. That's why we accept DeMorgan's law, because there's no way to disprove it. There's no combination that we could come up with that wouldn't work. Okay. And then here I'm proving the other DeMorgan's law, that not the quantity of A and B is equivalent to individually not A or not B. So again, I ran it through those same 4 tests, all the imaginable combinations, and I got these values right here. Okay, so that's an example of a truth table. Now, in reality, truth table, you might take out a piece of paper and write all this out. Okay, but anytime that you can show across the board that two Boolean expressions always result the same, you say that there are equivalent expressions. Okay, that's what it means for them to be equivalent or the same value. To help you do that, often you use a truth table. A truth table is just a way to show your work. So it's just the idea of writing out all the possible combinations, expressing them, and seeing the results. And as long as they all agree, then you can reach the conclusion that you have an equivalent expression. Many equivalent expressions have already been established and can be found on resources such as this link that I provided you. So, for example, in addition to DeMorgan's law, there's other ones. There's some weird ones like the absorption law. The absorption law says that if you have A and the quantity of A or B, that's equivalent to A. What does that mean? That means that like the A becomes meaningless. So I'm sorry, the B becomes meaningless, and it's just dependent on the value of A. So you could do that here, like with my little code segment, if you wanted to. Like you could write here A and A or B. Okay, that was one half of the law of absorption, and then the other half of the law of absorption was just an A. Now, you got to be a little careful, like the whole precedence thing with that concatenation piece. I'd have to actually put an extra set of parentheses around this. So what I'm saying is if you took that line right there and you just copied that print across the board here, so we'll have a total of 4 of them. Okay, so 1, 2, here's 3, and here's 4. What I'm saying is that this should work every time. Now, what do I mean by work? Well, I mean that the left Boolean expression should agree with the right Boolean expression according to the law of absorption. And so if you notice right here, it always produced the same result. It didn't matter what the values of A and B were. I guess I should have probably changed this print statement too, because now it's a little misleading. But yeah, so it's the same thing. This piece right here, okay, is what I'm doing on this one. And so it's not really DeMorgan's law anymore. This is now a law of absorption. But this piece right here, okay, is equivalent to simply A. That's kind of weird. Like that's saying that the value of B doesn't even matter, and it doesn't. And we could play around with this more. We could do some algebra and try to simplify it. The bottom line is these are established identities. Okay, you could go through and play around with any of these. You could try out the two distributive laws. You could try out the associative law, the double negation law. Any of these are fine. Okay, so experiment a little. Go through CS Awesome. You can use my code if you want to test any of them out. Like I just did here. But yeah, get creative and see what you can discover about these Boolean algebra properties.